2, 1. Alright, so here we are. We're going to keep talking about matrices, which we set up last time, and row operations, and in particular we're going to focus in on what we want to do when we perform row operations. So we're trying to solve systems of linear equations, and that's our goal. And now we're going to make things a little bit more precise and talk about, well, when we're performing these row operations, what are we really looking to do? What we're looking to do is get our matrices in echelon form. Okay, so echelon form has 3 requirements. Okay, as we saw, it's possible that when you do row operations, you get a big old row of zeros, and those rows we're going to put in the bottom. So all of the non-zero rows are above all of the 0 rows. Each leading entry, the leftmost non-zero entry, is in a column to the right of the leading entry below it. So we have what we usually refer to as a staircase pattern, and staircase is where this word echelon is coming from. And all entries in a column below a leading entry are zeros. So let's get some examples to codify this. So for example, this guy right here is failing to be in echelon form for a few reasons. So first of all, we have this row of zeros that's not at the bottom. And additionally, I have this 4 here. So this row has 1 as a leading entry, and here we see below it we have a 4. So this is failing this and that right there. But here now, row of zeros at the bottom, I have my leading entry right there, and I have this leading entry right there. So here we see the staircase pattern going on, and below my leading entries I have zeros. That's all there is to it. I'm just looking to make a matrix that looks like a nice little staircase. No more, no less, and all the zeros at the bottom. And note, the leading coefficients, I don't have any requirements of those being 1 or not. Some people are sticklers about it. I'm not going to care about that. Alright, so there we go. Now, something to make it a little bit more exciting is what's referred to as reduce row echelon form. Here, we're going to now require leading entries to be 1, and we're going to require that the leading entry is the only non-zero thing in its column. So this one, while in echelon form, is not in reduced row echelon form, because, again, the leading coefficient here is not 1, and there is a non-zero term above it. This one here is in reduced row echelon form. Here we have a leading coefficient, and they're all 1. We have our staircase pattern. We have our row of zeros. The leading coefficients only have zeros above and below. And now this thing over here is totally fine for reduced row echelon form because, well, we don't care about this thing. It's not a leading entry, and it's not, there we go, it's not of interest. So, worth noting that every matrix is row equivalent to exactly 1 reduced echelon matrix. It's usually referred to as the REF, the reduced row echelon form matrix. And that's might be useful information. Okay. So now that we actually have this terminology, let's go ahead and apply it to a matrix. So this one in particular is one of my favorite matrices, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we perform some row operations, we can get it in its reduced echelon form. So what you would do is start with this 1 here and use row operations to get zeros here. And then you would work over to this entry here and do the same thing. And again, these entries show up, and this is fine. This is in reduced row echelon form. Again, these are not leading coefficients, so they're not of particular interest to us. Okay. Now, given a matrix, we are going to use this language, pivot position, to indicate an entry in a matrix corresponding to the leading coefficients. So, for example, these things right here are the pivot positions. This is where the leading entries in the reduced row echelon form are. So any pivot position is going to then be referred to as a pivot column. So the first and second column of our matrix is a pivot column, whereas the third one fails to be because there is no leading coefficient in the third column in the reduced echelon form. Hey, exactly what I just said. There you go. Okay, now, obviously, this is a lot of verbiage, a lot of terminology. And, well, we want to have this because it's going to be useful to us. And it will be, because let's talk solutions. Because if I give you this augmented matrix here, I can get its reduced echelon form as follows. Here we see leading coefficient, zeros above and below. And again, we don't care about these ones because I already have my leading coefficients, and then everything else can be doing whatever it wants to do. Now note, 2 pivot positions, 2 pivot columns, and a corresponding system has a unique solution. That's pretty exciting. Let's look at this one. 623, 314. This reduced echelon form, here we see we actually have 2 pivot columns. The first one is pivot, the second one is not, the third one is a pivot column. And now our system here, however, is inconsistent. Now note, that's because one of the pivot columns here landed on the rightmost thing, which we know corresponds to the right-hand side. So a pivot column showing up there is going to guarantee a 0 equals 1 situation, which we don't want, because that gives me an inconsistent system. Or maybe you do want. Maybe you want your system to not have a solution. I don't know what you do in your spare time, but maybe that's what you like. All right. And let's get one more here. See, again, sort of the interaction between echelon forms and pivot columns with solutions. This one here, reduced row echelon form, again, is this. Here we have a row of zeros at the bottom, pivot column in the first and the second locations, and nothing in the third or fourth. And we have 2 pivot positions, 2 pivot columns, and the corresponding system is this, which we can then solve for x1 and x2 in terms of x3, meaning that we have infinitely many solutions. Now note, x3 is the variable that we can use to determine x1 and x2. x3, if we think about where x3 would be living, that's in the third column here, that wasn't a pivot column. Interesting. So the variables showing up in columns that fail to be pivot, we'll call those free variables, because they are the ones that we can use to determine the other ones. Right, because note, the pivot ones, right, are going to be isolated in their equations. There's only going to be one x1 that will show up. There will only be one x2 that shows up. Okay, and as we've sort of already pointed out, a system is consistent precisely when the rightmost column of the augmented matrix is not a pivot column. That means the echelon form of the augmented matrix cannot have a row of the form all zeros and then a non-zero at the right at the end. So we already pointed that out, but it's worth giving us this sort of final observation. This is a very powerful fact that's pretty easy to see, and that we're going to use and have a good time with. All right. And with that, that's the story on the echelon forms. Basically, when we have our matrices and we perform our row operations, we're looking to get them in echelon form because, well, when I go to a system and convert that over to my augmented matrix and perform my row operations and get my echelon forms, then I'm very easily able to communicate behavior of solutions, consistency or not, or infinitely many, because if I do not have enough pivot columns with the number of variables, I know that I'm going to have infinitely many solutions. Nice. Okay, so that's it for this topic. I will see you in the next video.